Good evening, everybody. Welcome to another monthly webinar, the series of the webinars that we organize, where we feature interactions with the authors of the articles published in iWonder. I'm Vinay Suram, and I'm a teacher educator at Ajim Premji Foundation. Let me take a moment to share a few words about what iWonder is. iWonder is a science magazine for middle and high school teachers. It features writing about the many dimensions of teaching and learning of science inside the classroom and outside it. This magazine is published in English, Hindi, and Kannada twice a year. If you are a practicing science teacher, we invite you to write to us. Uh, to do this, please send your idea in less than 100 words to iwonder@apu.edu.in. If you would like to receive the updates of each webinar and a free print version of each issue, subscribe to us by following the link displayed in the description of the video. You can also catch us on Facebook. Yeah, so coming back to our monthly webinars, as you all are aware, on the second Wednesday of every month, we invite authors of the articles published in iWonder for a live discussion. So for the webinar today, we have with us Yasmin Jayathirtha, author of the article Material Interactions, published in one of our earliest issues in June 2016. Let me share a few words about Yasmin. Yasmin Jayathirtha is a chemist and a chemistry teacher and is currently with Ajim Premji University, Bangalore. Yasmin has a fascination for how do we find out. So, Yasmin, thank you for joining us.
Thank you, Vinay, for having me. It's good to be here.
Yeah, so before we proceed on to our webinar, let me give our audience a brief overview of the format of this discussion. So, for the first 30 minutes, I will ask Aswin some questions related to her article. So, all of those who have joined us today are requested to type in their questions in the chat box. In the next 30 minutes, we will choose these questions and request Yasmin for her insights on those queries. So, yeah, let's begin. Ashwin, you begin the article by saying that there's a difference in the way physicists and chemists think about atomic interactions. Now, does this difference inform any way we understand the material world? Could you please elaborate on it?
Yeah, but because as you see, this came out of a discussion I was having with my husband, who's a physicist, and he said, "Okay, there are only four forces in nature," because I was talking about all the hydrogen bonds and things like that. So I said, "Okay, and as chemists, as far as we are concerned, there's only one force that we are primarily interested in, which is the electromagnetic interactions." But then the full gamut of those electromagnetic interactions leads you to all the variety of the way the materials are and the changing of that. One of the things that it probably makes chemistry difficult is that because we are looking at nuances of one particular interaction, it's not easy to get it down to, say, one equation or a simple formula and things like that. So we have to describe a whole lot, and which is why maybe very many people find chemistry difficult, because I've never found it. I love the subject and the interaction between the whole relationship between structure and function. But I know that people struggle, and this could be one of the reasons why they would struggle with that, which is why I wrote the article to say, hey, listen, there's really a beauty if you follow this out. Yeah.
That's interesting. So, it means to say there's a personal touch to the starting line then, the way the
Yeah.
article started.
Yeah, the way it's, yes.
So the grade 7th and 8th science textbooks usually introduce materials through informational properties. In your article, we learn how the properties of materials are explained by the nature of their chemical interactions. So, is there any right sequence of topics or concepts, for the students to develop an a broader view of this material interactions.
No, I see. I don't think there is a right sequence, but it pretty much has to be simultaneous, right? And the only thing I can say would be I want to explain how one of the first things that you perhaps have to have the students know is the whole. And I'm using the big term now, but it is the kinetic molecular theory. Really, to be able to have them think about, look, uh, there all these substances are made of particles, and how are these particles arranged, and with the states of matter, the three states of matter. So that is a very broad thing at this point. So you have the three states of matter, and you're talking about particles, and you're saying in a solid the particles are in particle interactions are at their strongest. In the liquid they become, I'm being nitpicking here, but I will be, that it's not that the interactions between the particles become weaker, it's just that the particles have more energy, so they can escape the interactions a little more, and they're free to move around. And then in the gas they have so much energy that they no longer can be pulled together. Uh, so once you've got that clear, in a way, looking at the giving of energy, changes of state, and we are lucky or in on this earth that we have a very common chemical which is easily available in all three states, water. So you can really play around, and all the children are completely comfortable with all the three states. So we should be playing around with it and looking at it. After that, you can begin to compare. Say, I did a project. Can I take a few minutes to describe that project? It was like a
Yeah, please,
prelude to the
please.
bonding that I wanted to teach. So I took, in my head, of course, I knew what was happening. So I chose six solids which essentially were exemplars of the six uh, bond types. So I had lead shot and zinc as for metallic bonding, iodine slash sulfur for simple covalent bonding, water and not water, they were all solids. So I had sugar for polar covalent, wax for simple molecular for sugar, and then wax for macromolecular not covalent bonding, and sand for giant covalent, and salt for ionic. Now, these are common, more or less common substances, and we began to study the properties. Now, one of the things that the textbooks do is that they're also not only talking about the interactions, not only the idea of the interactions comes second hand, essentially even the properties come second hand. Because they say metals are malleable, but you're not given somebody a lead shot and told them to bang around on it and hit on a piece of wax and hit on a salt crystal, hit a sand crystal and see what happens. That is dramatic. I mean, you can see that, look, these substances are behaving very differently. Wax squashes, the metal flattens out, and you can go on hitting. And the students are thrilled to see that how they can take that tiny lead shot and how thin and how wide they can make it, which they can't do with the wax. So we shouldn't be doing the properties secondhand. We should really be doing not demonstrations, allowing them to play with it. If you don't have time in the classroom, give it to them and tell them to do it at home and come back and talk to you about it. Make it homework so that it would be possible. And they do that homework also, I'm sure.
That's an interesting experience, actually. So, speaking of the sequence, what are some of the ways in which familiarity with the periodic table can help us understand or interpret or predict the material properties that we observe in the real world? Would it be more
The
effective to
periodic,
introduce the?
sorry. Yeah, go
Yeah,
ahead.
please, please
Finish
go
the
on.
question. No, finish the question.
Yeah, I mean, I just wanted to ask, would it be more effective to introduce the periodic table before or after the introduction to chemical interactions?
No, no. Periodic table, see, at the level of the what would be called the middle school, which would be the sixth, seventh, eighth, and even up to ninth and tenth, the periodic table has its place, but you can't structure your theory on the periodic table because the periodic table makes sense only if you're looking at the quantum mechanical model of the atom. But I would have the periodic table on the in the classroom, and one would keep saying, okay, we are looking at this, it's made up of what is it made up of, what does the bottle tell you is the formula, where are the elements, and have them become familiar with the periodic table. It doesn't help with the bonding per se, because with the interactions per se, but it will help. It will help much later. At the 11th and 12th, you can base your entire, you can know about the periodic table and get a whole lot from it, but not at this stage. But familiarity with the periodic table means that it's there and they learn to look at it. Then they will ask you, what are the numbers, and you can tell them. So at some point, you don't have to teach them anything because they're thrilled with what is the element which has my initial, what is the element, can we make up words with it, what is your molecular mass. So things like that. And they learn a lot without it being necessarily taught in some ways. So I would have the periodic table definitely in the classroom. And and then uh, talk maybe about the historical part of the periodic table, in the sense that because they're elements, you see, and most of the materials that we are looking at are compounds. So, in that sense, the periodic table won't be there. But even to say, even in elements, they got grouped together in their earliest form that these are alike. And then look to see, is there a way to order them so that they form a continuum? And the idea of the groups and the periods and all that, which came out of observation. It didn't come out of the theory. Fixing it came much later. And so, you should say that, look, so now where will you put your materials? How would you classify it? So, those kind of questions.
Okay. So, in your article, you built a gradual and elegant transition from covalent bonds to cations, anions, and then to ionic bonds using the phrase. I mean, this is an interesting phrase, pulling power. So, would you like to elaborate on what do you mean by pulling power?
Yeah. So there we really have to, in fact, break up some of the things that the textbooks do, because when we learn about the uh, structure of the atom first. And then when it talks about bonding, they talk about, which is a very valid thing, that because when the question was asked, why do elements react to form compounds? And many of them react spontaneously. Then Lewis came up with the idea, which is like, look, they try and get a stable, there is a stable electronic configuration. We'll come back to this. They will try and get a thing a little later, but that there is a stable configuration that the atoms get to go to. Then at that point, when you begin to look at it, and the reason one started with the covalent bonds was because I didn't want the idea that bonding happens only in compounds. And most textbooks start with ionic bonds. They say sodium has one, gives it up to chlorine, which has seven, it gets eight, and plus and minus. But then at that point, it's almost like the students are thinking that bonding means a compound is formed. But then you can start with hydrogen to say, look, if there are two atoms of hydrogen, and each has one electron, the hydrogens inevitably get together to, uh, they inevitably form a bond. Why is that? And then you can begin to talk about, look, the nucleus attracts the electron. It doesn't attract only one electron. It attracts the other electron also. And that is the pulling power, right? How much is the nucleus attracting the electron? Because we are saying that the electrons are being held by the nucleus. So why is it attracting only one electron and saying, this is my electron, this is the other hydrogen's electron? If there's an electron around, it will attract. And the moment it does that, then you have the idea of uh, pulling power. Then you say what in the nucleus would increase the pulling power. So you go like in hydrogen, the two hydrogens will pull, the two hydrogen nuclei are identical, so they pull on the electrons the same amount. So you have a non-polar covalent bond. So I use an analogy, and I have to keep telling the students, don't push this analogy too far, please, because then they'll take it to lengths that it's not meant to go. So I use a tug of war as an analogy. So you have this tug of war, you have the knot in the middle. If you're evenly balanced, the knot stays in the middle. If one is stronger than the other, the knot gets pulled towards that person's side. So that is that if one nucleus can attract the electrons more, which is the pulling power, it will form a polar covalent. To me, the sequence seemed like you don't have to work with compounds. You work with the formation of molecules rather than even in elements. But I must tell you that many textbooks use very nice descriptions. And one of the nicest have come is with a textbook which says formation of bond itself to say that Grace and Willie, because this is a British textbook, had two rabbits, and then they decided to share the rabbits, and each one had the rabbit in a hutch. Then they decided if they joined the hutches together, both the rabbits would have the space which only one of them was occupying. So both the rabbits would have the full space, which is a very nice description of a shared pair of electrons. And of course, then they are stuck together with it. Then it goes on to say, but the rabbits like Grace more than they like Willie. So they spend more time at Grace's side of the hutch than they do at Willie's side. So you'll see that the polarity comes in. Now you have to use some of these so that the students can visualize, but you have to point out that it's just a visualization and don't push it too far because it will break down at that point. So then of course, with my analogy of the thing, if somebody is so strong, then they just pull the rope off, and that is your ionic bond. And also, it is important because then you're kind of looking at there is a sequence in the bonding. That covalent and ionic bonds are not entirely different things. There is there is there is 100% pure covalent bond, yes. But when you come to an ionic bond, the moment the electron gets pulled away, the positive charge begins to pull it back. So you have a covalent bond, polar covalent bond, then you have what would be called uh, ionic bond with which has some partial covalent character, then you have an ionic bond. So it's a continuum rather than very discrete things. Because sometimes, uh, and the trouble that our students have had, and other teachers should tell me whether they have, is that when you start with the ionic bond, and then you ask them to say what will happen with water, they have a tendency, because the electron things will work out, to write water as an ionic compound. And then you have to explain, no, if they can share, they will share rather than take away, because it takes more energy to take away and things like that.
Those are some interesting analogies, but the caution that you made about not overdoing it, I think that needs to be kept in mind as well.
Yes, yes.
So, well, speaking of this pulling power and going a step ahead, you also talk about different electron clouds and different geometries in molecules. Can you briefly explain the meaning of electron clouds in covalent bonds and how do different geometries shape properties of molecules?
Mm. Oh, no. Biggest distractions that, biggest not distraction, the biggest problem with the way things have been presented in textbooks is also the structure of the atom. I think they've got caught up with the orbital electrons orbiting around the nucleus. So you keep showing that. But the real picture now is that we don't know where the electron is. So we know that there is a space in which there is an electron. Now, though I cannot at this point I tell the students I cannot explain it to you. I'm sitting and saying, don't think that the electron is in a particular space, and it's just there. And what happens if I have a nucleus with the electron uh, uh, around it? Because there are two or three problems with the way the picture is drawn. One is that they begin to say, don't the electrons collide with each other when they form a bond? Because you're visualizing your little planets going around the sun,
Yeah.
which is a terrible analogy as far as it goes. Then you have the feeling that it is a two-dimensional structure because we draw it flat. So now I have to say, look, the electron is three-dimensional. The electron is all around the nucleus. And so you have to help them visualize some of those things. And then at that point, you say that, look, okay, you have a hydrogen atom and there is the electron, which is all around the nucleus. We don't know when, we don't know where, it's moving so fast that we can't tell. What we can only see is this blur of uh, negative charge around it, which is like a cloud. Hmm? Now, if another hydrogen comes near it, what will happen to that cloud? Will it stay the same way? Or will it move towards the other nucleus? And then you have this interplay between electrons repelling each other and uh, uh, nucleus pulling on it and so on. What will happen? So I also point out that people came up with this whole idea of the what is called in textbooks the VSEPR, valence shell electron pair repulsion theory, is that when you have clouds of electrons, they try to get as far away from each other as possible and still stay as close to the nucleus as possible. And what is the geometry which comes in? Now, again, there's a very elegant experiment which I found in a book which I happily do, which is to take balloons, not the round ones, but the long ones, the cylindrical ones, blow them up, and then you can twist them around. And when you twist two balloons together, you will have four arms, and it goes into a tetrahedral shape automatically. And then you do one more and you will have six, and it goes in what is the octahedral arrangement that the VSCPR does equally. Now, the fun part that comes in the experiment, which all the students enjoy, and you have to make sure that you twist them really well, is you carefully poke one of the arms and deflate that pin, put a pin and make a hole in it, and that goes off. And how will the five rearrange themselves? What kind of a formation does it form? And then you will find that this is geometry. It's coming out of how, in the three-dimensional space, substances arrange themselves. So you can do some of these experiments also.
That is really interesting. So, before we proceed further, if our audience have any questions to ask Yasmin, please send them to us in the comment sections. Ashwin, continuing our discussion, uh, what is it about plastics that makes it difficult for microorganisms to break them down? Now, can our knowledge of these chemical interactions help us design biodegradable polymers that can substitute plastics?
Yes, in fact, they have. And when I was doing this material interactions and when we looked at it, so there are two parts to the question. One of the things that the designing that we looked at, and I found this whole very interesting thing called polyethanol, which is a water dissolving plastic. And you, depending on the number of OH groups you leave in the polymer as you make it, it can either dissolve in cold water or hot water or boiling water at various degrees. And I believe they make hospital uh, waste bags out of those for hospital linen and so on, bed sheets and things like that, so that you can put them into the bag and then you don't have to take them out, so nobody is exposed to microorganisms. You put them in the washing machine, and in hot water the band of polyethanol dissolves, the bag falls apart and the clothes get washed. So yes, you can design them. That is one part of it. The other part is nature is a much better designer. So as we are putting plastics into the environment, you find that people are the organisms are looking to see there's all this material lying around in the thing, and at some point some mutation, and people, the two threads that even that two strands that even that is research is taken. People have found microorganisms which have been digesting uh, PET plastic, that is polyethylene terephthalate, the commonly known as PET, the various Shri PET bottles and things like that. And then Frances Arnold, she got the Nobel Prize for that, did this whole mutation of forcing the enzymes to evolve, forcing mutations so that enzymes can be evolved so that uh, you can make enzymes which can chew up the plastics. I think long ago, a scientist from, is it Exxon or somewhere called Anand Chakravarti, bred microbes which could eat up oil spills and worked on that. This is many, many, many years ago. I haven't heard about it after that. So I have somebody I did my PhD with, one of my uh, lab mates, who's now a a molecular biologist, and he said, you know what, all this gene splicing and things like that, you don't need to do. You just go to environments and swab, and I'm sure you will find a microorganism which is used, whatever is lying there, as a source of, and you need to find out how to culture it and how to get it going. And now one is seeing a lot about that. But the biodegradable itself, I suddenly had a question when I was thinking about it, not now, but earlier, which was like, when we talk about biodegradable, what do we mean? Does it become carbon dioxide and water? Or does it break down into small pieces, which is good because then the whales and the cows and all are not eating it. But then now with microplastics causing such a lot of harm in the environment, are they becoming microplastics or are they completely degrading? Now that is a question that needs to be answered also.
True. So, coming to a classroom scenario, studies suggest that teachers often find it challenging to teach chemical bonds because they cannot be seen directly. Now, how would you suggest introducing chemical bonds in middle school so that the students understand the physical meaning of the concept?
See, that is, in a way, when we talked about materials also, and we talked about the states of matter, and if we are making them look at it, we are making them, we are in a way talking about interactions, no? Between particles. So I'm using the word interactions, I'm not specifically using the word bonds. Then you begin to say, where do these interactions arise from? And we talked about the various, we can talk about there. But we need to link it to the properties, right? We need to say, we need, in a way, starting with the kinetic molecular theory and using that to explain the states of matter, you're also training the students to think about what cannot be seen and predict properties that you cannot see. You're going from the macroscopic property to the microscopic. Now, we've always done that. Chemists have always done that. And so but you have to train students to do it. You have to say, what do you think is happening here? When when I'm giving energy and the water is and steam is coming out, what is happening? Where are the particles going? What do you think is happening to the interaction between the particles? Then you introduce bonding by saying, is it still water? So has the bond between hydrogen and oxygen broken? I think that's a very common misconception that when people think steam when steam is formed, hydrogen and oxygen bonds break, because we've never taught them how to visualize and model. And I think it is a skill that should be got explicitly. What do you think is happening? If there are 10 particles here, how do you think they're interacting? And what are those particles made of? Are we breaking the covalent bond here? Or are we just breaking the interactions between the particles? So the moment you allow them to visualize and say, how do I go from the macroscopic to the microscopic? And then point out that the whole tetrahedral nature of the methane molecule and the carbon atom and the benzene structure and all that came out of these kind of looking at the macroscopic properties and then saying what is the structure which fits them. Now, I also go over and over the scanning electron microgram pictures, which show you the molecules and say, now you can see atoms. And I was thrilled with the idea of IBM, using that stem, putting neon atoms to form IBM and all that. But then I'm more thrilled with the idea that, hey, it was predicted. You're now seeing it, but it was predicted, and you're seeing what was predicted. So that is a greater power. And you teach the children now, how do I make sense of all this data that I have? What model fits? So it is a skill that has to be specifically taught, and have them question them, let them go wrong, let them work out, ask why not, which property doesn't it help with, and so on, and then work with that.
So, in your article, you also share very real life examples of all these chemical interactions, like making roti atta or paneer, or ironing out creases in cotton cloths, etc. Now, would you elaborate on the importance of offering such examples?
Very much so, because I got hooked on to chemistry for that, for a very simple reason that the school I was in, we had just done acids and bases, and we did have labs in the school, so which was nice. And then I went out, when I had lunch, I spilled uh, some of the curry on my white uniform blouse and went to wash it off. At the moment I put soap, the turmeric turned red. I said, okay, this is acting as an indicator, and it clicked for me. And from then I have been fascinated. So for me, yes, I think when it clicks for somebody, and I've just been, as you know, I teach student teachers at APU, and so I've been looking at readings, and in a way, I uh, came across this. Uh, Not an article, it's an essay called Having of Wonderful Ideas. It's by Eleanor Duckworth, who is a student of Piaget. And she's talking about that how do you expose them to thinking about the world? How do you, science should give them the tools to find out about the world that they inhabit. And these examples will allow you to use science to explain the world that you are inhabiting. So if you talk about nylon and you talk about nylon interactions, and when you tell them, okay, look, when you hang a nylon sari, what happens to the water? And then you see that it all drains out and drips down, while your cotton clothes remain wet and you can't squeeze out the last of the water from it. And it doesn't drip off and it will take a while to dry. You are then, and you've talked about hydrogen bonding and you've talked about water bonding with polar molecules. You're also helping them to see it in operation, as it were, not in the lab, but all around you. And that is when you begin to really see that chemistry is not just the little bits from the textbook and the laboratory, not everywhere.
So, normally popular teaching aids or videos tend to explain interactions by ascribing intent to the atoms. So, as in phrases like what an atom wants or needs are
Mm,
common. For
mm.
example, atoms are trying to reach the most stable
Yes.
state that they can.
As you notice,
You know,
even I use that analogy till I changed it. Yes.
yeah, they become stable when their valence shell is filled.
Mm.
So if atoms don't have this octet arrangement, they will want to reach it by gaining, losing, or sharing electrons via bonds. Now, would you like to comment on this?
Yeah, as I said, it is a very common thing that all of us do. But at some point, I think the mistake that we make is to talk about it as atoms. So it's not atoms. If I have an isolated hydrogen atom, it's not trying to do anything. But if there are many hydrogen atoms together, so the intent, or not even the intent, but when hydrogen atoms are together, the tendency is to what? Okay, it is in the interaction that it comes about, not by isolated atoms. And I think that is the mistake that we make, whether we teach physics or chemistry or whatever it is. When we talk about things, we talk about isolated things, we never talk about interactions. And we so it is, and all of science in some ways lies in the interactions. So we should be doing that. Ascribing intent, it makes it simple, and then I correct myself to say, well, it doesn't know. So it was. So when I'm teaching at the higher stages and I'm talking about equilibrium, so I say the equilibrium moves to the right because there is less a product, and I say, okay, it doesn't know that. It is just that you have to point out that it is a net movement and not a real moment. So it's not just chemistry, because even in biology, when you talk about osmosis, you talk about water molecules moving to the more concentrated solution. But you have to point out that it's a net movement, but describe in a short form as something happening. It seems a shorthand, and then you have to keep repeating that it is a shorthand, and atoms don't know.
Yeah, true, true. So now, continuing with the discussion on models, but moving from away from textbooks to learning by doing. So, how effective is it to use physical models or have students build models to understand chemical interactions? No, is it like, are there any certain models which are more effective than the others? There seems to be a bit of network issue, and Asman will be back with us. Meanwhile, if you have any questions, please do type it in the comment sections, and we can hear what Ashwin
Yeah.
has to say about it. So, Yasmin is welcome back, Yasmin.
I'm so sorry. I think my
So, could you
internet
please
connection
repeat
just
what you
went.
said earlier?
Yeah, yeah. I was talking about the fact that the models might be as simple as I use pens when I'm talking in the class to say, okay, I have two electron uh, pairs. How far can they get away? This is to talk about the geometry of molecules, and everybody will say 180. 3, you come to uh, 120 and a trigonal. Then I say 4 and they'll do the square planar, that is 4. And then you show them the tetrahedral and they say, yeah, that is further. So a model can be as simple as that. It can be the chemical models. It's helpful because when you're trying to visualize, it's helpful to be able to see rather than trying to see in 3 dimensions. Because I draw on the board, it's in 2 dimensions. Then the models can be, like as we said, building models. Uh, Building models with uh, so at some point having them build models and say how will you show what it's like. Say if you're building DNA models, if you're building the model of a protein, where will you put in the how will you put in the different kinds of interactions and so on. Yeah, all of those help because in a way they're trying to make something tangible, uh, but as long as we remember that it's just a model. I mean, it is a model. It's explaining the reality and it works. It's good, great. But the moment it stops explaining the reality, you have to say there's something wrong with my, which is why the whole series of uh, bonding, models of bonding that there are, and so that you can look at it. Yeah,
Okay.
yeah.
No, one of the interesting phrases that I read in your article was that no, that if bonds were the only interactions between particles, all substances would be either solids or gases. So, can you elaborate on these non-bonded interactions, particularly in the context of biomolecule systems and life processes? And how can these interactions be introduced at middle school level or
Well,
high school
as we
level?
said, the interactions are already introduced at middle school levels when we are looking at the states of matter. Because if we are looking at what is a compound, we are saying, look, hydrogen is bonded to the oxygen and nothing is happening to that. I might not be talking about what the interaction in the water molecule is, but I'm saying there's something there. Because if I have isolated water molecules and then they will be hanging around and nothing much will be happening. Then, if I have, say, graphite or carbon or something like that that I take, or sand, then you have your various bonds and you have your giant covalent structure, or you have your ionic structure, positive and negative ions coming together. So, where is the middle? Where is the liquid? So at that point, you have to say, no, this is not a bonding, but because of this so called pulling power and because it distorts at various levels, various amounts of distortions happen. And then you can talk about your various non bonded interactions, uh, including coming to hydrogen bonds, which are important, and and you really show the fact that in DNA molecule, for instance, and I've just been teaching it, so this analogy has been striking because I read a phrase which said that the backbone of the DNA molecule, that is the sugar phosphate backbone made of covalent bonds, doesn't break down, so the DNA. So the DNA molecule stays intact, so the genetic information stays intact. But the hydrogen bonding between the bases means that you can peel it apart. And Velcro is a nice example to use for that. And then, so with not too much energy, you can peel it apart and form it back again. And so you're not breaking down the integrity of the compound, but you are changing the states in which they're formed or it's dissolving. So to explain any of these processes, you will need your non-bonded interactions.
No, there's a question from one of our viewers, Vijayta Raghuram. So
Hmm.
she asked, how do you help students visualize the position of electrons in terms of probability rather than an absolute position?
I wouldn't do it with, say, ninth and 10th standard students. But with the plus two students, I would talk about look, where will I find you at 12 o'clock on a Monday? Or, well, I use a particular time, which is 11:15, which is the snack time. Where will I find you? So then they say, well, on the way to have snacks. And then you point out that, yes, mostly you will be there, but there might be a day when you're absent. There might be a day when your teachers kept you later in class. So that is the whole idea of probability. Or you might be a little further ahead because you got left early. So the idea that it is somewhere in that region and you can only get 99% because to be 100% certain that the electron is somewhere there, you need the whole universe. And that can be mind blowing for students. But to say that 99% you are around here, you are within this region of your habit and where you're drawn to and where you're held. And I'm not ascribing intent to the electron at that point, but the electron being held by the nucleus is within that region of space because of the energy that it has.
So we have another question from Shlok Dinni. From grade 6, there's a particular question regarding the biodegradable things.
Hmm.
So, is there a permanent substitute for plastic usage?
Because we have been finding so much about plastic pollution and all that, we forget why plastics were invented and why people have embraced the use of plastic so much. We've forgotten the advantages of plastic. And so at some point, uh, the fact that it's waterproof, so your food doesn't spoil. With gunny sacks, you had to make sure that it didn't get wet. With paper, when you bought it, it tore. The fact that it is very strong and very light means that your transport costs are lower. Glass breaks and can be harmful. Hmm? Plastic bottles are safe. Metal containers are heavy. So we've forgotten the advantages of plastic. So maybe what we should look at is how do we reuse? How do we sequester? How do we use less? Which I think should be the first thing to say. How do we not overuse? How do we use as much as we need but not there? How do we not say, people because of the advantages. When I go to shops and I take my cloth bag, the shopkeepers tell me, you're the only one who does. Most people say, give me more bags. And they yell at us if we don't give bags. Now I think people are getting more educated about that. So let us hope. Let us not throw away the plastics because they're doing a great deal of good in terms of food losses itself. I'm sure the plastics have cut it down quite a bit in terms of losses with waterlogging or getting wet, getting mold, getting things and so on. So I wouldn't want to throw it away. But it's also true, it's a quite a funny thing because it is a generational thing also, no? So some of my students, when I gave them an article to read on plastic, said it says plastic is good in this article because they've only read about plastics being bad. So I said, yes, please look at the advantages of plastic and the disadvantages and see how we can mitigate those rather than looking at that. So I would say that we are looking at biodegradable things. We can say, how much can we reuse the plastic? Biodegradable plastics is good. Will we pay more for it? And can we say that at that point, can we bring in this conversation to the children also? Will we pay more for it to save the earth? Will we use less to save the earth? And use a little inconvenience to save the earth? Hmm? And bring in that conversation. And children are highly, I don't want to use the word moral. Children have a very strong sense of justice. So I'm sure they will say, yeah, it's not fair that we throw it around and it harms other things and we should work with it. How do you recycle? How do you make sure that it doesn't harm? So I think those are the conversations that we should be having.
So there's another question from one of our viewers. So it says that you mentioned that dispersion forces are very weak by themselves, but a lot of them can cumulatively be very strong. So strong that they allow a dead lizard to remain stuck on the ceiling. Now, how do chemists discover such things? Whether an observation is caused by a few very strong forces or may not very strong forces? What kind of experiments do
No,
they do?
many not very strong forces. Yeah, I think this is what is called the gecko's foot. And at some point, people were looking, and I don't think they'd like themselves to be called chemists. They were probably physicists at that point. So anyway, so at that point, when you look at the fact that that is also another thing, no? So you begin to look at. mm, mm, and okay, I'll come back to that as other observation later on. So when you look at the gecko and then you say that how is the gecko able to run up the ceiling? What is holding it up there? Strong enough that gravity isn't pulling it down. But you know they can fall. So you know that gravity does act on them. And then they're making attachment only by the foot. So, if you have very a few strong forces, the gecko will have to use a lot of force to un unstick itself from the wall and move. But it doesn't do that. So the very many weak forces, it is like, again, I would use Velcro as an example, that the Velcro spread over that whole thing holds your shoes together as much as the lace does. But you can pull it apart very easily if you go about the right way, start with the right direction. So very many weak forces can be as strong as very many. And if we want to go completely metaphysical at this point a little bit, to say at the very edge of where the electrons of the gecko's foot get the tendrils, I mean the gecko's foot, they did an electron micrograph and they found that it's made into it's like a fan and the tips get finer and finer and finer and you have this huge surface area. And when the very tip meets the table, where is the table? Where is the gecko? Where is the ceiling? Where is the gecko? Because the two have come together and formed an electron bond.
That's nice. In middle and high school, science is taught as general science, not as separate subjects as biology, chemistry, and physics. And it's most of the time often taught by a single teacher. Does this provide any opportunity to introduce chemical interactions as a way to appreciate that life is made up of chemical processes? Any suggestions on how teachers can go about this?
No, in fact, I think we should teach it that way. But I disagree with you when you say that it's taught as general science. It isn't. The book might be a single book, but there are separate chapters on physics, separate chapters on chemistry and biology, and it's not like they're very related to each other. It's not like they draw upon each other. It would be nice if they could draw upon each other. And if a single teacher is teaching, it then brings in all that opportunity to say, hey, I was talking about this molecule in biology, or I'm talking about this process or the digestive process, and this is what's happening out there, and it's a catalyst, then you're talking about catalysts and chemistry, and this is a catalyst just like that. The same fundamental principle holds, and things like that. That is the way it should be, but it isn't very often that way.
In your experience, what are some of the most common misconceptions about chemical interactions that you encounter in school and college students? Could you also share some pedagogical strategies to recognize and challenge them in schools?
Uh, you mean how would you teach interactions? Uh, I'm kind of trying to figure out what the question is asking in some ways. Uh,
So it's more
so
about
the
what are the
real
kind of
world
ideas the
examples of
students carry.
the real world examples, like I said, I pointed out that if we are looking at things that dissolve in water and don't dissolve in water, uh, what are the kind of substances, what are the interactions out there, why wouldn't they do it? So one of the very clear yeah, there is always more than one interaction, and that is the difficulty of chemistry that one as students also look for, unfortunately, because they've been trained that there is one correct answer, and you're sitting and saying, look, in chemistry it's a balance of, even if you look at atomic structure and things like that, it is a balance between the nucleus attracting the electrons and the electrons repelling each other. It's not it's not a single thing. So you need to find the balances out there. And you need to think about two or three things which are happening simultaneously. I think making them think about it rather than giving them an explanation, making them, asking them, what do you think is happening here? Is the force here greater or is the force here greater? Is the force in B greater or is the force in A greater? Why would you say that? Why do you think A dissolves in water but B does not? So having them think through and articulate their thinking, I think helps bring that in, and pulling it in there. It has to be, because if it's given as information, and which is why students find it difficult, that it's given as information and they're going, and their eyes are already glazing because you've given so much information out there. And then they're sitting and saying, I'm supposed to remember all that. And then I sit there and say, okay, all the formulae. So do you know the formula of water? Yeah, H2O. How do you know the formula of water? I use it very often. So, okay, use this very often and you're going to know this one also. Which other formulae do you know? And how do you know it? Why do you know it? And then to say that, look, you have to use it to be able to remember it, and use it in context rather than try and remember by rote, because you can't, unless, because if you've learnt it by rote, unless you get the right trigger, you're not able to get it out. And we've seen that not only in chemistry, we've seen it, I'm sure, with young children and multiplication tables, that they'll ask you, what is 5 into 6? And they don't know. But you know your 5 times table, right? And they'll go 5 into 6 is 30, 5 into 7 is 35, and they go past not recognizing that the answer is there because they've learned one thing by rote. So to put it into context and to sit there and then say, look, take a guess, and that is the most important thing. You can be wrong. And I might show you something which says you haven't explained this in here. But it's okay. It's not that you're wrong. You're still trying to figure out what's happening. And so that there is no one right answer. And can we think it through? Can we do this? What experiment will show us whether you're right or wrong? And all those building mental models, we have to take away also, I think, take away the fear of being wrong, because that does inhibit students quite a bit, because they feel there is a right answer there and I should have got it. But some of the questions that I've seen, say in an IGCSE or things like that, don't say what is the reason. They say, can you suggest what is going to happen? Which means that it's leaving it open that it could be more than one thing, or what are the things that are likely to happen. So that more than one thing and any one of them can be correct. So you also have to be careful about the language that we use with students.
So extending this a bit further and with very specific reference to the chemical structures. So you mentioned that many students find the many chemical structures in their chemistry textbooks challenging. Now, how do scientists come up with these structures? Are there any ways in which these methods of discovery can be replicated in a classroom, even with a simple experiments or simple structures or thought experiments?
Yeah, simple thought experiments, yes, because at some point you begin to talk about how did the tetrahedral nature of the carbon, of the methane molecule or carbon atoms come about. And so we are talking about even before spectroscopy. And Labelle and Mantov, I think I'm using it, came up with the idea that look, you have methane and you substitute one of them with a chlorine. That's fine. But the general way we draw on a two-dimensional thing is a square planar one, right? And looking at it. Can you give me half a minute? I'll get to three pens and show you what I mean.
Yes, please, please.
Yeah. So now we are looking at something like this. Okay. So they come up with this idea. And I do this in the classroom because I feel that rather than a model, something like this makes it more real for them. Then you say you replace this top one with a chlorine, and then the second chlorine can go either at 90 degrees to it or it can go at 180 degrees to it. That means that their properties will differ. But Lebel and Van Hoff kept trying to make and never got more than one compound. And because their properties differ, you should be able to separate them. But they never got more than one compound. So they said, look, it should be tetrahedral. And as you can see, it should be tetrahedral because then all the hydrogens are identical and it doesn't matter which one you replace. So that was among the first ones. But the really, because now I've been doing those molecules of life, and I long ago had looked up with, uh, there's a scientist called Emil Fischer, and he worked out the structures for all the hexoses, glucose, fructose, and all the things, and there are 16 of them. And he worked it out by chemical this thing, what reaction it gives, starting with an assumption that he made about the structure of one of them. It turned out that he was right about that because when the X-ray crystal structures and all came, it turned out to be right. Otherwise, he would have got the mirror image of it. And then he worked it out. Now, that is a beautiful example of using logic, evidence, and then saying, if this is the structure, then this reaction should happen, this compound should form, and working with that. To show that elegance, as I told you earlier, to me, the you can now find out the structures by looking at the STEM pictures, the scanning, tunneling, electron microscope pictures. But the pictures are fabulous. But for me, the fact that they're only showing you structures as you already decided what they were is even more fabulous because you did it without knowing. You deduced it, and that is lovely.
That is interesting. So far, the conversation has been completely engaging and very beautiful. And the last part where you showed a model and explained about it, four pens, and that's very, very, very engaging. So, before we end the conversation, Any parting thoughts? Anything that you would like to say?
I would, I've been thinking about science education, particularly in the middle school, for quite a while because I've been teaching. I've been lucky enough to be teaching in a place where I'm in control of what uh, uh, how I wanted to teach. And not all teachers are so lucky. I'm hoping that the NAP is bringing in some things uh, that can change some of the education. That can we move away from content and can we move to the processes and science? Because really, it is the sheer amount, and when I'm teaching the student teachers also, I can see that at that point they say, but I need to cover this content. And yes, you need the content to be able to think about processes, but the content shouldn't rule. And how do you bring in the fun of science? How do you say, hey, look, go and explore and tell me what you found out? And then can we find the science? You told me something that you observed, and can I find the science in that and help you explore it further? Can we change at least the middle school science? I'm looking at sixth, seventh, eighth, ninth, and tenth. Okay, you need to do your 10th exam, and can we sit there with a very, I mean, I would change the assessment system also, but I'm not going that far here. But I'm sitting and saying sixth, seventh, eighth, and I'm using those ages in particular because they're old enough to be able to abstract a little bit. They can visualize, they can do I have a minute to use slightly this thing? So uh, I do say, example, I do a project with indicators with uh, the equivalent of fifth standard students, and where I will take an indicator and ask them, has the color changed, the idea of acid base, and the indicator changing color, and so on. Now, I wouldn't do it. So, when they add indicator to milk and things like that, so is it acidic or basic, all the substances, and so on. Now, I do it with the fifth standard students. I wouldn't do it with very much younger students because with very much younger students, when you add an indicator to milk, yes, the color may not change because uh, it's acidic or basic. It may change because the white of the milk has made the color different. But if I ask, did it change in a way that you didn't expect it to change? The older child can say yes. It didn't become like when I mixed paint, but it became a different color. But for a younger one, it has changed. And I shouldn't be telling the younger one, no, 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 it has not changed. Can't you see that? Because what the younger child is seeing is a change. And I shouldn't deny that. But I can't push that younger one to see it in the way I want the child to see. I want him or her to see it. So we should also use it at the right age. You shouldn't push it beyond what they can get it because then they have to say, okay, I'm accepting what you're saying. But if they have gathered enough to think about evidence and evaluate, you can say people did this experiment and this is the evidence and this is how they evaluated the evidence. They can at least evaluate the second-hand evidence and say, were they right to say that or not? And so on. So there's one more which I just found out. I haven't tried it out yet, but I want to. And let me share it with you all. This is somebody has called what he calls an analogy experiment for atomic Rutherford's experiment, which comes in the eighth and ninth, and people find it difficult to explain. So has a whiteboard, props it against a table props it a little high on with a little channel in between, underneath, so that a coin can go through, and then puts a ball at the back, something heavy, and then has students come in and push coins at it, and the other students look to see which coins go off and which come back. It's a beautiful, elegant, analogy. He says, I don't tell them what it's an analogy for. I just do the experiment with them. And then they find out that there's something blocking there, and these coins are coming back, and the rest of it is empty space, and
Going
coins are
different
going
direction.
through. And then he says, when I teach the Rutherford experiment, they say, oh, this is what it is an analogy for. And then they work with it. So I think as teachers, we should be looking to say, how can I bring this within the grasp of the students? So I'm thinking all the time because I should be thinking all the time because I'm looking to say, how would I explain that? How did they find out? And does it make sense to me?
That's very interesting, especially the last word that you mentioned
Oh,
about
that's a beautiful thing. Yes.
the Rutherford experiment.
Yeah.
Yeah. So, Asmin, thanks a lot. Thanks a lot for joining us today and having this, very engaging conversation. So, and all of those who have joined us today, thanks a lot. We may not have been able to take all your questions. Apologies for that. But still, if you have any pressing questions for Asmin, you can send them to us at iwonder@apu.edu.in. We'll do our best to get them answered. So join us again for the next webinar on 9th March of 2022. And for all of those who have not yet subscribed to iWonder it, we hope you do so now. Thank you.
Thank you very much for listening to me.